2y, power rule.
And then times d with respect to x
Of y. What do y'all think? Does that look okay? Do you see any mistakes? Does that look all right to everyone? Does anyone have a question on where any of those pieces came from? Let's recap. We took the derivative with respect to x of this. This is composition. The outer layer was sine. Derivative of sine is cosine. Leave the argument the same. Times, chain rule, times. Now you take derivative of what's inside, which is a sum, so you have to do both of them separately. When you take derivative of the first one, it's a product rule. So you do derivative of x with respect to x times y, plus derivative of y with respect to x times x. Done with the product rule. Plus, now this is just a regular old power rule, 2y, then derivative of the y itself with respect to x. Done with that. Good job. Very good. That, if you can do that derivative, you understand what's going on. Like that's about as bad as they get. Yes?
The x on the, when you did the product rule, that last x, where
yes.
did you get that?
Okay, so remember on a product, right, you have two things in a product. The formula is you take the derivative of this first, then you multiply times this. Then you add to it the derivative of that, right, but then times this at the end.
Oh, okay.
Right? That's, a lot of people forget that because they get so fixated on making sure they get that, get that derivative right here, that they forget, oh, I've got to finish the product rule off and bring that x back in. Other questions? Okay, very good. Volunteers for the next one. This, where are we? Right here? Any volunteers for that one? Oops. I have to get a new volunteer. You've proven yourself. No? You want to go for it? Okay. So we have subtraction, right? So I can just put a minus now? Okay. And now you're about to take the derivative of the x squared y. Tell me how you're going to do that. It's a product rule, so we're doing this one right now. So we're taking the derivative of the first piece. Yep, good.
Multiplied by y.
Times y, good. Plus
over dx.
dx of what?
Of y.
Of y
Times x squared.
times x squared. That is a perfect application of the product rule again. The derivative of the first one times the second one plus the derivative of the second one times the first one. But there's something that is wrong with our notation right now. Can you see it? We're supposed to do what? Subtract whatever this derivative is, right? The way I have it written, the way it is now, I'm subtracting, but I'm not subtracting the whole derivative. So I need parentheses here and here. Critical that you get that. Right? Because you're subtracting whatever that derivative turns out to be, you want to subtract the whole thing, right? So if that derivative turns out to be two terms, which it is, two terms, you have to subtract each term. So the parentheses around that are important. Questions? Okay, we're done on the left side. Who wants the right side? Okay, let me find who's going to do the right side then. Alan? Where's Alan? Alan, how are you doing, Alan?
Good.
Did you follow this?
Yeah.
You didn't have any questions? Okay, so tell me the next thing to write. Equals, good. I was seeing if you were going to do that or not. Equals. What do you got? 0, right? Now, I don't need to write 0, right, Alan? I don't need to write 0, but I'm going to, because if someone's looking back going, where did that come from or where did that go? I just want to represent it. You want to keep going?
Yeah.
Okay.
The derivative of 2 d over dx
Yeah, how do you do this? This is kind of weird. How do you do that? You're not going to do product, right?
It would just be
2. All right, so Alan's saying this is just going to be 2. It's just 2 because, look, we're differentiating with respect to x, right? If you differentiate with respect to x, you don't have to worry about that whole d dx thing because you know it's going to turn into 1. So just treat this like a good old-fashioned 3 weeks ago derivative, right? That's the way I think you should look at it. So that just becomes what, 2, you said? Minus 2? So that's this one. You want to keep going, Alan?
plus dy dx.
Yeah, plus, now this one you can't get around. This does not turn into 1, but this is just the derivative with respect to x of y, which is dy dx. And we've got it. This is our derivative. Or I'm sorry, this is the implicit differentiation has been performed. Okay? We're not done. Our next step, let me clean things up. All right, just kind of clean up some of my notation. Here we have, let's see, cosine of xy plus y squared, okay, times, and then a big parenthesis here. This one turns into 1. 1 times y is y, plus the derivative with respect to x of y is dy dx times x plus 2y and then times dy dx. Close the parenthesis. Minus parenthesis. Oh shit, did we never take that derivative? Hold on. We never took these derivatives, right? We never did. When we did the product rule in here, right? We wrote down what it was, but we never took the derivatives. So we can do that in the next step. That's fine. So we're right here, aren't we? What's the derivative with respect to x of x squared? That's your traditional, like, old school derivative, right, from a few weeks ago. So that's just what? 2x, and then times y. And then plus this, which is dy dx, right? Can't change that. Times x squared, close parentheses, equals negative 2 plus dy dx. Okay. Would you all agree that there's some room for error here? Right? Like you can mess a little thing up and it make a big difference. I hate grading these. I absolutely hate grading these. It's because finding the mistakes are so hard to find because there's so many places that it can happen. So that's why it's important on the test for you to show your work. Because if you don't show work and you just give me a wrong answer, I take off a lot. But if I see it all and I say, oh, they didn't put the parentheses, right? Everything else is correct, then I don't take off as much, right? We're good? Okay, what's the goal now? Get dy dx by itself. Shit, right? You should be saying shit. You don't have to say shit. You can say something else. That's okay. But you shouldn't be happy because the dy dx that we need to isolate is here, 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 and here, right? Now, this is good. It's just sitting there by itself, right? This one is inside of a parenthesis, isn't it? So I have to release it from the parenthesis to ever get it isolated. And to do that, I'm going to have to distribute the negative through. That's not so bad, right? This one and this one are in here. I cannot pull it out as a GCF because it's not here, right? It would have to be in all three terms. So the only way to release these two from the parenthesis is to do what? Multiply the cosine through to all three terms. And then you release it from the parenthesis. All right, so this is going to suck. All right, yeah, let me do it. I'm taking this entire thing and I am distributing through here, like that. That's the only way to free the dy dx from the big parenthesis there. So when I multiply this cosine xy plus y squared times y, nothing happens. They just sit next to each other, right? So I'm going to put the y in front of the cosine xy plus y squared and put it in front. And then plus, now I have to do that whole thing times this. So I'm going to, again, put all that stuff out in front. And then when I go here to here, again, all that stuff, 2y dy dx, I'm going to just put it out in front of the cosine of xy plus y squared. The algebra, students will try and do some other weird algebra to try and get dy dx, and normally it's some like shortcut and it never works. You have to crank out the algebra here. Do I have any questions on the distribution of the cosine through the parenthesis? No? I'm done with this, right? Now here, distribute a minus to both of those. So minus 2xy minus dy dx times x squared. So those just become negative. Then the other side of the equation. All right. Well, at least I have freed the dy dx's from the parentheses, right? Now what I can do is I can figure out which terms have the dy dx in them. So this has a dy dx. This has a dy dx, right? That has a dy dx, and that has a dy dx. There are 4 terms with dy dx in them. Right? There's 4 of them. Terms, when I say terms, what do I mean? Terms are separated by what? Addition and subtraction. So what I'm doing is I'm trying to figure out what terms between the additions and subtractions have the dy dx in them. This one does, that one does, that one does. That's a term. That's a term right there. Once I've identified which terms have dy dx, I'm going to move all of them to one side of the equation. And anything that does not have dy dx goes to the other side. So since I have 3 of them on the left side, I'm going to leave these here. I'm going to bring this one here, right? So I'm going to bring this one over that way. And then what over here does not have dy dx? Well, that, right? And that don't have dy dx. So I'm going to take both of those to the other side. So this is going to go to the right side, and this is going to go to the right side. So let me write what I have. I have this right here, dy dx times x times cosine of xy plus y squared plus 2y dy dx cosine of xy plus y squared, okay, minus dy dx x squared. And then I brought this one, the one here in red, I brought it to this side, which makes it minus dy dx. That's all my dy dx terms on the left. Equals, now on the right side, I have negative 2. That was there to begin with, wasn't it? But what comes to join this? What joins that over on the right-hand side? You have this right here. So over there, it's going to be minus that, right? So minus y cosine of xy plus y squared. And then what else joins over here? The minus 2xy comes over here and becomes plus 2xy, right? When you bring it to the other side, you change the sign. We're 2 steps away. What was the point of that? So you can dy dx out, factor it out as a GCF. So all of these over here, all what, 4 terms, all 4 of them have dy dx in them. So I'm going to factor dy dx out. When I pull dy dx out of this, I'm just left with the x cosine x, bless you, xy plus y squared, plus when I pull dy dx out of this, I have 2y cosine of xy plus y squared. And when I pull dy dx out of that, I get minus x squared. And when I pull dy dx out of this, I get what? Minus 1. Don't forget it's minus 1. Don't just say, oh, it goes away. It's minus 1, because you would have to be able to distribute this back and get all 4 terms, right? And that equals the right-hand side, negative 2 minus y cosine xy plus y squared plus 2xy. What's my final step? You want to get this by itself, right? So you want to get rid of all that, so you have to do what on both sides? Divide that whole thing. Yeah, you said, I understood. So this whole big ugly thing, right? You're going to take this whole thing and you're going to divide by it, right? You're going to divide it over here by itself, and then over there you divide it as well. So I'm going to just divide it over here. It's x cosine of xy plus y squared plus 2y cosine of xy plus y squared minus x squared minus 1. There we go. So it goes away over here, right? It goes away completely. And you have your dy dx alone. So that's your answer. On your test on Tuesday, I plan on giving you one of these on the test, but it'll be an easier problem than this, and you will not have to solve for dy dx on the test. All you have to do is differentiate correctly. So I'm not going to ask you to isolate the dy dx, because I told you nothing we do today will be on Tuesday's test. So today is about doing more complicated problems and solving for dy dx. All right? Well, this is a more complicated problem. I wouldn't give you something like this. But this, I've already erased the line you could have stopped at. But I think this one right here is it. Right? We've taken all the derivatives here. It would have been that line right there. What are y'all thinking of this implicit? Questions?
I have a question.
Yes.
Can you show us what you mean if we do the next problem, like where to stop at?
Where to? Yeah, I'll do one. Yep, let's do one, and I'll tell you where I would want you to stop for the test on Tuesday. That was a nasty problem right there. I will admit it. Okay, so let's do. How about we do this one? X cubed plus, now this is going to be a very simple one. X cubed plus y cubed equals 1. And I want us to find y prime. So now I just used a different notation. It's the first time I've done this. When you see y prime in this class, we mean dy dx. That's what we mean. So I'm going to differentiate both sides with respect to what variable? X. Okay, I do it on the left, and I do it on the right. On the left-hand side, I have 2 terms. So I split that up into 2 different derivatives, both of them with respect to x. And the left side, I'm going to put 0. Heads up. Oh, it feels good. Oh, I better get that. All right, what's the derivative of that first one? 3x squared, right? You don't have to do the whole chain rule thing because you're differentiating with respect to x. It's just your traditional old derivative. 3x squared. This one, however, you have to worry because these aren't the same variables. So you first do your power rule, 3y squared. But then what would come next? dy dx, right? dy dx. I didn't write it, but what I had been writing before was the derivative with respect to x of y, right? But every time we've done that, it just turns into dy dx. So I'm going to stop writing this, and I'm just going to say, okay, this is just 3y squared dy dx. And then equals 0, right? That's where I would want you to stop on the test on Tuesday, right there. Just do the implicit differentiation and stop. If you watch my homework solution videos, if that's something that you've been doing this semester, you'll see that if I were doing this problem in homework, I would write it like this: 3x squared plus 3y squared. And then instead of saying dy dx, since dy dx is equal to y prime, in my homework solution videos, I write that. I just choose to use the y prime instead of the dy dx. Just forewarned. You've been forewarned if you watch my homework. I do it a little different on the video. Right, because that means the same thing, right? That's y prime, so just replace that with y prime. That's that. Okay, I have a question for you. I would like for us to do this problem again, but this time I want you to do this. I want you to find dx dy. This time, what are we differentiating with respect to? To y, right? So I'm going to put dy on the left and equals dy on the right. So I'm differentiating with respect to the variable y on both sides. Let me do the easy one. The right side is 0. Right? Derivative constant is always 0. On the left side, I take derivative with respect to y of x cubed, and then plus the derivative with respect to y of y cubed. Now look at that for a second. This one is no longer our nice, good old school derivative anymore, right? Because these two variables aren't the same. But this one is, because these two variables are the same, right? So it's like they're going to trade places. This one's just going to turn into what? 3y squared. This one is not going to be just 3x squared, though. So let me do this one first. This one is just going to become 3y squared equals 0 over there, plus in between. This one, I have to do the power rule, 3x squared. But now, times, I'm differentiating with respect to y, I'm differentiating the base that's here, right? X. And that's dx dy, isn't it? That's dx dy, which is what I asked you to find. Right? See the difference between the two? Y'all sure? Now I'm not solving for it. I'm just writing it down, and then we'll stop here. So again, this idea is that I'm going to take the y value and I'm going to change it by just a little bit. And then you're supposed to figure out how much the x value is going to change if I do that, and then take their ratio, dx over dy. That answer is different than doing it the other way around, where I say I move x a little, how much does y change, and then doing that ratio. Questions? Sure? If there are no questions, I'm going to do a third one. Well, wait a minute. Is there anything even possible for me to ask? I've already asked what dy dx is. So I've already used the x variable on the bottom, right? I've done dx dy, so I've already done the y variable on the bottom. Is there another possibility that I could ask? Doesn't seem like there is, right? But I'm going to. I want to know, I want to find dy dt. All right, let's put a little asterisk because we are now moving into a new place here, okay? Because I'm differentiating with respect to what variable? T. But t does not appear in the problem, right? T is not a variable within the actual equation. So this is saying, look, if I change t, right? If I change the value of t by just a little bit, I want to know how fast y is changing. But there's no t in here, right? So what we have to imagine is that the t is like a clock in the background, and you have, this is like a relationship where you've got some motion going on and you've got a clock running. And so we're trying to figure out basically at a certain instant in time how fast the y is changing. You'll see. Let me just crank it out. So I'm going to differentiate with respect to t. I'm going to differentiate the left side of the equation. And then I'm going to differentiate with respect to t the right side of the equation. The good news is the right side is still 0, okay? I think I told you this. I don't care what calculus class you're in, ever, in the rest of your life, what math class you're ever in, the derivative of a constant is always 0. That's never going to change, all right? It doesn't matter with respect to what variable. This constant is not changing, right? A constant doesn't change. So if I ask how fast does a constant change, you say 0. Sum, let's split it into 2. Derivative with respect to t of x cubed plus derivative with respect to t of y cubed. Right? Splitting into 2. Both of these do not have matching variables, right? Both of them. So both of them have to be done with chain rule. None of them can just be the simple, 3x squared or 3y squared. They both need the chain rule. So this one will become 3x squared times what? dx dt. Good. Plus, this one becomes 3y squared, but then times what? dy dt. And that is still equal to 0. Questions on that differentiation? Neither of these two go to 1, right? Neither one of them do. Now, are we going to be able to solve for what we're asked to solve for? Do you see that in here somewhere? Right there. Could you algebraically get it by itself on one side of the equation? Probably, yeah. So I'm not going to, but we can, right? I'm going to give you another one. You ready for another one? Yes.
Just leave it like that?
Well, if I asked you to find this, what you would do now is solve. You would get this by itself. Let me do it. So you see this dy dt is that's a term, right? This does not have dy dt in it, so I'm going to move that to the other side. So my next step would be 3y squared dy dt equals, if I move that to the right-hand side, it becomes negative 3x squared dx dt. With me? And now finally, to get dy dt by itself, I just need to divide 3y on both sides. So to get dy dt by itself, I take negative 3x squared dx dt, and I divide the whole thing by 3y squared. And that is my answer. It's good. It's good. Oh, God, damn it. Would you mind? Thank you. It's the end of the week. All my markers are running out. You ready for the next one? How many of you have ever seen the following formula in some other class? Anyone ever seen that before? No? Yeah? No? Anyone know what that's called? Really? Only a few of you have seen it? Normally when I ask this question in the calculus class, about half of this class recognizes it. Chemistry? Chemistry? It's the ideal gas law. Okay, so this is a formula that works all the time. Okay, it's a physical property of the universe. Okay, and that is pressure multiplied times volume equals N times R times capital T is temperature. Now N and R, I'm not a chemistry person, but I believe one of these is the gas constant and the other one is the number of moles, if I'm not mistaken. Someone in chemistry could correct me there. I believe that's number of moles, and I think this is the ideal gas constant or something. So these two numbers together are just a constant, right? T is temperature, volume, and pressure. So let me explain this. If you have a container, okay, if you have a container and you have, let's say, a gas inside this container, then think of a soda can, right? Think of a soda can. You have the temperature of the gas in there, right? The temperature of the gas. You have the volume of the gas, or the volume of the container, and then you have the pressure. And they're all connected to one another. If the temperature goes up, right? If this side of the equation gets bigger, then what must happen over here? Either the pressure has to go up or the volume has to go up, right? One of the two. So there's this back and forth. If you make the volume smaller and leave the pressure the same, then the temperature is going to do what? Go down, right? So this is why when you have a soda or something and you pop it open, I don't know if you've never noticed this before, but you get this rush of gas that comes out, right? That little stream of air is usually colder than the air around it. And if you've ever felt that before, opening a beer or something, you feel the cold, right? It's the release of the gas. What happens is, as soon as you drop the pressure, right? You open it, the pressure's gone. As the pressure drops, the temperature comes up. And actually, this is the way an air conditioner works. Do y'all know how air conditioners work? I mean, we turn them on. We love them in Texas, right? We need them in Texas. Would y'all like to see it or no? Do we not care? It's this law. So the way an air conditioner works is that you have outside your house or somewhere buried in your car, okay, somewhere inside of your car, you have this thing called a condenser. I don't know if that's spelled right. Who cares? So you have this condenser, and what it has in it, it's got all these coils in it, and it has a liquid. It's called Freon. And Freon has this really, really cool property that